Welcome back to the workshop for one last video in section 2.2, equivalence relations. Now that we know what an equivalence relation is, we want to consider the set of elements of a set A that are all related to one another. So we talked about transitivity. I can move from one to another using the transitive property. And how far will that get me? Will that get me through the entire set? Is everything related to everything? Yes, no, maybe. But that's what we're going to look at for this example. So if we have an equivalence relation R on the set A with some element of A. So R is an equivalence relation on A, and here's some element in A. The set of elements of A that are related to X is called the equivalence class. Equivalence class containing X. And it's denoted by X with brackets around it. So X. Okay. And we would say that X is the set of elements Y belonging to A such that X, actually, let's see here. Well, it doesn't matter. If we have an equivalence relation, order doesn't matter. So you could say X is related to Y or Y is related to X. Doesn't really matter because it's an equivalence relation. So it's, again, symmetric. All right. So the equivalence class is the collection of things that are all related to one another. Okay, if we choose this particular representative, X, then we would say all of the things that are related to X. All right. So let's take a look at an example of this. We've already considered in our previous example a specific equivalence relation. And so we're going to revisit that equivalence relation and take a look at some of the equivalence classes. For some examples, for some sets, you'll be able to determine all equivalence classes, and it's really quite nice. For this example, we won't be able to determine all of them. So our relation for this example is X is related to Y whenever the largest prime divisor of X equals the largest prime divisor of Y. All right. So we want to describe the equivalence classes for these three numbers. So let's go ahead and do that. For X equal to 176, right? We want to describe all of the numbers that are related to 176. So it's all of the numbers that have the same largest prime divisor. So the first thing that we want to notice is that 176 is equal to 2 to the 4th times 11. So 11 is the largest prime divisor. Excellent. So since we have 11 being the largest prime divisor, the equivalence class containing 176 is simply the set of all numbers, so all numbers with largest prime divisor of 11. Excellent. This is fine. It's a great oral description. However, it's not very mathematical. It's not a very descriptive set. So let's try and use set builder notation to give a better demonstration of what numbers are in this set. All right. Well, the first thing is that we're going to need a factor of 11. So each of these numbers that are in the set have the largest prime divisor of 11. So they all have to contain a factor of 11. Beyond that, they can have essentially anything you want, any number of factors of any prime number less than that. So what I'm doing is I'm writing our collection of numbers in their prime factorization. And when I write them in their prime factorization, that allows me to specify that the factors that they contain are only those that are 11 or smaller. So what prime numbers are smaller than 11? Well, we have 2, 3, 4 is a product of 2 and 2, so it's not prime. 5, 6 is a product of 2 and 3, so it's not prime. 7, 8 is 2 cubed, 9 is 3 squared, 10 is 2 times 5, so 11 is the largest prime divisor that we're interested in. So any factorization, any prime factorization of a number that belongs in here is going to contain these factors at most, okay? But there could be any number of these factors. So 2, I could have to any power. So I'm going to write it as 2 to the a sub 1. And then I'm going to have 3 to the a sub 2, 5 to the a sub 3. Let's see here, 5 to the a sub 3, 7 to the a sub 4, and 11 to the a sub 5. So 2 to a power, 3 to a power, 5 to a power, 7 to a power, and 11 to a power. Now I included an additional factor of 11 out front, guaranteeing that I have a factor of 11. In this way, I can say that each of the AIs must be numbers, integers greater than or equal to 0. If they're all 0, then the number is just 11. And as I build up more and more and more, as I make these numbers non-zero, I just get larger and larger numbers. And this is for I being between 1 and 5. So A1 is an integer greater than or equal to 0. A2 is an integer greater than or equal to 0. In particular, they're non-negative, right? A1 is non-negative, A2 is non-negative, A3, A4, A5 are non-negative integers. So this is a description of the equivalence class containing 176. Excellent. So let's do the same thing for x equal to 225. Well, again, the first thing to note is what is its prime factorization? Well, this is 3 squared times 5 squared. So 5 is the largest prime divisor. With 5 being the largest prime divisor, the equivalence class containing 225 is simply going to be any number that can be written as a product of primes that are 5 or smaller. So that means we've got 5 to guarantee at least one factor of 5 times 2 to some power times 3 to some power times 5 to some power. Now, any of those powers could be 0, 1, 2, 3, 4, and so on. If A3 is 0, I still have a factor of 5 because I added that out front. So again, AI should be a non-negative number. So this is, if we haven't seen it before, this is the notation for the integers. And we end up with several different sets that we can talk about with regards to the integers. So one of them that we probably actually won't see in this class is Z star. And that's all of the integers except for 0. The same thing goes for R star or Q star. These are all that set of numbers without 0. So Z star is the integers without 0. R star is the real numbers without 0. Q star is the rational numbers without 0. We also have Z Now, whether it's a subscript or a superscript changes, I think I've seen both. So we could have ZE, which is all of the even integers, ZO, which is all of the odd integers, and we can have Z greater than or equal to 0 and Z less than or equal to 0. And of course, you could choose to not have the equal to there as well. So these are all different subsets of the integers that we'll be interested in. So in this case, in our example, we're interested in the integers which are greater than or equal to 0. So this is non-negative integers, this is non-positive. But of course, if you want the positive, you would specifically be talking about 1, 2, 3, 4, and so on. These are also called the natural numbers. And you also have Z negative, which is -1, -2, -3, -4. So there's all of these different subsets of the integers that we might be interested in. And you would find yourselves using some of these throughout the semester. In particular, evens, odds, and occasionally you'll run into non-negative, non-positive, positive, and negative. And of course, the standard integers. All right, so just some notational stuff going on there. So when I'm looking at this guy, these are the non-negative integers. So each of these exponents is a non-negative number. That is, it is allowed to be 0. So for I between 1, 2, 3, between 1 and 3. Excellent. So the equivalence class containing 176 is all numbers with these prime numbers in them, prime factors. 225, the equivalence class containing 225 is the equivalence class containing all numbers that can be written as or in their prime factorization having a largest prime divisor of 5, having a largest factor. So then finally, for x equal to 132, we want to note what the prime factorization is. Well, 132 is equal to 2 squared times 3 times 11. So the largest prime divisor is 11 in this case. But that's the same as what we found up here, the equivalence class containing 176. So I don't have to do any work, right? They have the same largest prime divisor. So the equivalence classes are the same. So the equivalence class containing 132 is a set of numbers that can be written in this way. 11 times 2 to the a sub 1 times 3 to the a sub 2 times 4 to the a sub 3 times 4. Why did I include that? 5 to the a sub 3 times 7 to the a sub 4, 9, 8, 9, 10, 11, a sub 5. There we go. Where AI is non-negative, and we're looking at all of the i's from 1 to 5. So this is just a way for me to very quickly say that A1 is a non-negative integer, A2 is a non-negative integer, A3 is a non-negative integer. All right, that's going to take a while to say, but I can simply say that all of them are non-negative integers. Okay, done. But this, we said, is the equivalence class containing 176. So from that, we would say, well, of course, 176 and 132 are related to one another, so of course they would belong in the same equivalence class, and hence the equivalence class containing them is the same. So that's absolutely fine. That's perfect. So one thing that we want to note here is that two equivalence classes, A is equal to B. Two equivalence classes are equal if and only if. Really quickly, that will be shorthanded to IFF in the future. So two equivalence classes are equal if and only if these representatives are related to one another. If and only if A is related to B. So let's move that guy over just a little bit. Excellent. So in this case, right, 132 is related to 176, as we already said. All right, but that's the end of section 2.2. So that's all that we have for now. I'll see you guys back in the workshop for section 2.4 very soon.